Suppose L is some language and X is a string in that language. A finite automaton accepts the language if, for any string in the language, the finite automaton will process X and end in an accepting state. But finite automata could not accept many different languages, so we introduced pushdown automata. A pushdown automata accepts L if, for any X in the language, the pushdown automaton processes X and ends in an accepting state. Now, note that it might also end with an empty stack, but as we showed, the two types of acceptance are the same. But while pushdown automata include more languages than finite automata, there are still languages they can't accept. And so we introduced Turing machines, and we can imagine letting a Turing machine process X on the input tape. And note that a finite automaton accepted a language if our string led to an accepting state. A pushdown automaton accepted a language if X in the language led to an accepting state. Since Turing machines don't have accepting states, we'll need a radically different concept for accepting a language. A Turing machine accepts a language if a string in the language leads to the halt state. But what if X is not in the language? In that case, our Turing machine might crash, definitively rejecting X, but it's also possible the Turing machine might run forever. In that case, we'd never know if X is in the language or not. Even if our Turing machine ran for 10,000 years, it's possible that if we let it run for one more second, it would enter the halt state. Since any string X is either in the language or not in the language, we'd want a Turing machine to reach a decision about X. And so we say that a Turing machine recognizes a language if it halts or crashes on any input. And note that this is different from accepting a language, which only requires that the Turing machine get to a halt state when X is in the language. Now, if it halts on the input X, then X is going to be in our language. And if it crashes, X is not in our language. So the question, is X in our language, will always be answered. One problem is that if a Turing machine runs forever on input X, we don't have any obvious way of determining that beforehand. So if the Turing machine runs for a very long time, it's possible that it will run forever. But it's also possible that letting it run for just one more second, one more move, will cause it to either enter a halt state or crash. So how can we tell? So one possibility is input sanitization. We'll create a second Turing machine. This second Turing machine will take our string X and determine if the original Turing machine will eventually halt or crash or run forever. If it will halt or crash, then it'll pass the string onwards. Otherwise, it will reject the string. Note that if the sanitizer rejects the string, this is not the same as deciding the string is not in the language. Instead, it means the Turing machine won't be able to decide if the string is in the language or not. It should be clear that the second Turing machine can't simply process the string. If X would cause the first Turing machine to run forever, it will also cause the second Turing machine to run forever as well. So instead, the second Turing machine has to consider the string X and the structure of the first Turing machine. So we want to chain two Turing machines. A regular Turing machine, which will process some string X to determine if it's in the language, and a sanitizer S, where S will evaluate X and determine if it will cause our Turing machine to run forever. If it will, then our sanitizer rejects X. Otherwise, it passes it on to T and then lets T decide on whether X is in the language. Now, since it only passes along strings that will cause T to eventually terminate, either by halting or crashing, then given some string X, X is either rejected by S and never reaches T, or X is approved by S, and then T determines whether X is in our language or not. And so while our initial Turing machine might run forever on certain inputs, our chained Turing machine TS will not. Or will it? So if S is a Turing machine, or really any automaton, it's possible that some input X might cause it to run forever. So we'll want another sanitizer S' that will reject any string that causes S to run forever. So while TS might run forever on certain inputs, TSS' will not. Or will it? And it's possible that some input X might cause S' to run forever, so we'll want another sanitizer S" that processes X and only hands it off once it's determined that S' will either crash or halt on X.
Of course, there might be some other input X that causes S" to run
forever, and so on and so forth. To avoid this endless regression, we'll introduce one more idea. If the Turing machine halts or crashes, then in general, the tape will have a finite number of symbols on it, and the tape head will be at some position on the tape. So suppose X causes the Turing machine to halt, where we can start at our initial state, our blank square, and whatever X is, and eventually derive the halt state, where some string is followed by a blank. So the tape has string Y, and the tape head is positioned just after the last non-blank space. We can interpret the state H as the Turing machine accepting string X as part of the language. But we can also interpret the tape string Y as the output string produced by an input X. In other words, our Turing machine has computed f of x equals y. And we'll use the notation t of x to indicate the Turing machine given input x. So given some Turing machine, we can ask whether it halts or crashes on any given input x. This is equivalent to asking whether a function can be evaluated on any input. The function value might be defined for the input, and the Turing machine halts, or the input might not be part of the domain, in which case the Turing machine crashes. But it's also possible that neither will occur. This actually motivated Turing's original paper with the question, what numbers can be computed as function values? We'll take a look at that next.